Now that we've installed Keras, we can jump into some machine learning. But first, let's set a baseline of understanding of some core statistics. If you're already comfortable with linear regression and gradient descent, feel free to skip to the next video to see how to implement these in Keras. For those brave souls still with me, let's get statistical. This module will cover some of the background on linear regression, one of the simplest ways to model data. You'll learn how NumPy can implement this basic tool. Suppose you've got some real valued data in two variables. That is, you have a bunch of pairs of decimal numbers, maybe representing the price of a dinner and the mass of the food. A simple starter of bread is probably very cheap, while a large serving of stew is expensive. You can of course plot these values on a grid, such that the y-axis indicates the price and the x-axis indicates the mass. It's easy to show this with matplotlib. Let's do a simple example. First, import matplotlib and NumPy with some shorthand. Do plt.ion to make plots show up as soon as you execute them. Our data is stored in a NumPy array food.npz. This is fake data, so don't worry about the exact values. You can load it in by doing np.load and the file name. But this gives a dictionary. To get our array, we have to ask for the first one, arr_0 by default. Each row is then a data point. The first column is mass, while the second is cost. To do a plot, you can simply call plt.plot with your x and y arrays. If you want to label axes, use the plt.xlabel command, or similarly for y labels. For finished graphs, this is a must, but if you're only checking for a trend real quick, it's probably not necessary. You can visually see there's an obvious relationship between the mass and the cost here. As one increases, generally the other does too. If you increase the mass by 10 grams, how much might the price increase? You should be able to imagine drawing a line through the center of these data points, and you could probably compute the equation of that line. This would give you a model for predicting price given the mass. Drawing a line is great if you have a sharp pencil, but we want something a little more formal and automated. Most lines won't be perfect matches. Can we derive a way to compute the least worst line? Suppose you have some line. A single data point is off from that line by some amount. You can measure this by computing the vertical distance from the point to the actual line, as that's the difference between what the model predicts for that input versus what your data says. Let's call this the error. If you added up all the absolute value of the errors between your data and a single line, that would sort of summarize how good a fit it is. For reasons we won't go into in this course, statisticians often prefer to square the error of each data point and sum those up. The best line is then the one with the least squared error, shown by this equation, where m is the slope of our line and c is the y-intercept. The trick then is knowing how to find m and c such that you minimize the error e. The two most common approaches to this are the normal equation and gradient descent. Let's implement the former in NumPy. The normal equation is a way to directly compute the slope and intercept of the best fit of your data. The mathematical details of why this works are beyond the scope of this course, but you should know that it applies when the number of variables and number of data points isn't too large. When the matrices get too big, say more than 10,000 columns, the equation is still valid, but it takes a long time to compute. Here's a quick Python implementation of the normal equation. Create 100 fake data points based on a line with slope 2 and intercept 0.5. So we'll be looking for those values in our computation near the end. np.random.random makes uniform random values between 0 and 1, here serving as our x values for data points. We also need a column of 1s to serve as the multiplier for our y-intercept term. This whole array we transpose so that we have n rows and 2 columns. The errors will be uniformly distributed between plus and minus 0.1. To compute the true y values based on the parameters and errors, we use the NumPy dot function for a matrix multiply, hitting the x data points and 1s with the actual weights, and then just add in our errors. Some errors will be positive, while others are negative. The normal equation itself fits on a single line, albeit a long one. First, you need to take the inverse of x transpose times x. Dot can do the multiply, and lidalg.inv can do the inverse. Following the formula, we multiply, which is dot again, another x transpose, and finally multiply in the actual y values. The result should be our computed weight. To take a look, just print both the original and computed weights. Pretty close, right? Let's draw the resulting line against our data as well. Just make two dummy points based on x equals 0 and x equals 1, compute the predicted y value at each using our new weights, and then draw a line between them. In Matplotlib, we'll plot two sequences. First the data, ignoring the all ones column, as blue circles, hence BO, and the prediction, which is really just 2 points, as a green line. There are more statistics you can compute to verify the significance of your model, but for now, just check that the line seems to match the data. This method is nice because it directly computes the weights with a few linear algebra routines. There's no guesswork. It's a mechanical process with a known result. But its strength is its limitation. These linear algebra operations take too long when faced with a huge amount of data. To overcome this, scientists developed an approximate iterative solution called gradient descent. The details are beyond the scope of this course, but the general process is simple. Pick a random set of initial weights and compare the error as well as the gradient. Think of the gradient as which direction we should nudge our weights to be more correct. With that information, you can adjust your weights slightly to improve the model. Then you compute new errors, rinse and repeat. Essentially all complex statistical models rely on some form of iteration to find weights. There are numerous variations, but it's important to remember that they work a little bit at a time. Okay, now that we've gone through the laborious process of manually implementing linear regression, let's see how Keras makes this a snap.